Now remember, in the exercises before, we used G1 as our target, and we regressed upon G1. And it was an integer, so this was no problem. But now we want to use it as a categorical variable. And we won't use all 20 possible or 21 possible classes from 0 to 20, but rather we will group them in four different classes. So the first class will be all the points from 0 to 5, and then we will have the second class all from 5 to 10, third from 10 to 15, and fourth from 15 to 20. And we will call this variable y. Then afterwards we will delete G1, because this would be a very good predictor for our variable y, but obviously we don't want to use that. So now we will build our classification tree, and then use also cost complexity pruning, choose the optimal alpha, and examine the tree and variable importances as before, but this time for a classification tree. So let's create this variable, and it's very easy. So in this variable y, which we put inside our data frame, we will store a factor, so a categorical variable, which cuts the variable G1 into 4 classes, and it will cut between 0 and 5, 5 and 10, 10 and 15, and 15 to 20. So exactly as described here. And so it goes from 0 to 5, from 5 to 10, from 10 to 15, and from 15 to 20. So let's do this. Then we'll delete G1 from our data set, and let's have a look at it. Now you can see y here. Then we can build our classification tree just by using the apart library as before, and I said max that to 3, so it's easier to observe. And now you know that here in the end we will get the probabilities for, or let's have a terminal node here. So in this terminal node we will have the probabilities for all the classes. So we have 4 different classes, and this is the probability for the first class, and this is the one for the second class, for the third class, for the fourth class. So let's plot this. And yeah, as shown before, here the probabilities again. Now this is a little different because all the values are rounded and can be a little bit confusing. For example, here failures greater or equal to 1 is rounded from 0.5, so that's very confusing actually. But that's just how it is. So let's just work with it. But these values are actually rounded a little more reasonable. So yeah, this is how you end up with it for 4 classes. This is the relative proportion of observations of this class inside this this node. So in this end node, 0.07 is the proportion of class 1 observations, and so on. Okay, now let's find our optimal value for alpha when we want to prune our tree. I have the settings just as before, just change the target variable here, and we can find our optimal alpha again. So let's have a look at the out of sample and cross-validation error, and we see that it's lowest at this alpha value here. So let's use it. Also, you can check if it's understood that you want to classify. So this is the classification tree, so it will use the accurate measurements. So let's use the alpha value inside our tree. You will see that we end up with a much larger tree than the one I described before, because that was horrifically underfitting. And now this tree we can't really read anymore, because it's gotten so small, the box has gotten so small. But we don't need that, because we could also just have a look at the terminal nodes here. Okay, same goes for variable importance. We can use just the same lines as before to get the importances. Now you see that for classification now, the most important values have changed. So here now failure was in the regression number 1 here, and now for our groups classification, absence is the most important variable. Now we can have a look at this in percent. And yeah, we see also that now it's not that clear anymore what is the most important variable, because before that, when we compare the variables, failure was at 27%, I guess, and now absence is the most important with just 10% importance.
In exercise 3b, we will use test train splitting to calculate our in-sample and out-of-sample classification errors. I use the same splitting as in the previous sessions. And now I will train the classifier using the optimal alpha value. Now I want to show you what happens if we just call the predict function using our classifier and the training dataset. So this would be a prediction of the in-sample data. And you can see that our predictions come in the form of 4 columns, and the rows are all the predictions that we made. So for every observation there is a row, and for every class there is a column. And within the column, or within each cell here, there is a probability. So what is the probability of the observation number 341 to fall in the class 1? So this would be roughly, or 9% roughly. Now, class 1 would contain all the grades between 0 and 5 points. The highest probability of all classes is contained in class 2 for this observation. So we would expect this observation to fall in class 2. So to have a grade between 5 or 10 points. And we do this, or this is the case for all the observations that we predicted, or the predictions of all the observations. Now we want to calculate the classification error, which is the proportion of the target values, so the true values, that are not equal to the corresponding elements in the prediction. So basically, how often do we predict correctly relative to all the predictions that we made? Now, if we want to use just predict, we couldn't calculate this matrix classification error, or it would be very difficult to do this with the different probabilities. So we'll use type equals class as an input of the predict function to tell the predict function that we want to choose the class with the highest probability. So the predict function will return a vector of the class with the highest probabilities for all the observations that we predict. So then we can compare the predictions, for example, class 1, then class 5, then class 4, I mean, we don't have a class 5. So the different classes basically for all the observations with the actual classes they fall into of the training set. So let's do this. And we see that our training error is rather low with roughly 32%. So in 32% of the cases, our prediction does not match the actual class they fall into. Let's do the same thing for our out of sample estimation. And we see that this error is now much higher with 49%. So 49% of our predictions do not match the actual value. So you might think, well, isn't that roughly as bad as just choosing random, so 50-50? And this would not be the case, because when we choose randomly, we would randomly choose one of 4 classes. So the performance of a random selection would be 25% and not 50%. So this is actually much better than selecting randomly. And obviously it should be, because this is the whole reason why we would train our classifier. Okay.